Hi friends, in this video we will talk about welding inverters again, but I assure you it will be interesting. This is an average good welding inverter with a current of about 160 amperes. It weighs 4.4 kilograms. This one, the smallest one, almost full-fledged welding inverter from China. The weight after a little reworking is about 1.7 kilogram. The maximum current is about 90 to 100 amperes. I shot as many as 2 videos about this inverter. In the first video, we examined it, studied the feeling, the work in general, the advantages and disadvantages. In the second video, I remade it, that is, reduced the minimum current to 20 amps, calibrated the scale, added an output choke and a soft starter. You will find links to all videos in the description. Anyone who looks at this inverter, first of all, is surprised at the size. It looks like a toy, but it's really a welding device, and in general doing its job quite well. Since then, I had been haunted by one question. Is it possible to make a full-fledged inverter, but even smaller, so to speak, device which will surpass the Chinese one? So I thought on theme, and now the finished unit is in front of you. It is completely homemade and is a full-fledged welding inverter with an output current of up to 80 amps, but you can get to 90 to 100 amps without increasing dimensions. That is a complete analog of our Chinese friend. The height of the Chinese inverter is 12.5 centimeter. The homemade product is only 8 centimeter. The length of the Chinese is 20 centimeter. The length of the homemade housing, including the terminals, is about 15.5 centimeter, and including the terminals is slightly more than 18 centimeter. The width of the Chinese is 8.5 centimeter. My version is slightly wider, 10.5 centimeter. The Chinese device initially weighed around 1,560 grams. After the reworking, it began to weigh about 1,700 grams. Homemade is much easier, only 1,100 grams. The Chinese one gives somewhere around 90 amps, and at the homemade product, the maximum current is limited to around 80 amps. As housing, I use the mini power supply unit from the computer. I will immediately answer the question, why did I do this? Solely in order to understand whether this is possible, so to speak, purely sports interests. Therefore, let's not discuss in the comments the practical meaning of this homemade product. After all, some people send cars in space for the sake of sports interest. Here, it's about the same. Naturally, if we are talking about such small sizes, we need to sacrifice something. In our case, this is cooling. So this inverter is not designed for long-term operation, but we can use to the end several electrodes in a row. Making an inverter from the beginning is extremely unprofitable. Good original parts are expensive, and you need experience in technique of the pulse power supplies and power electronics. In general, it is better and more profitable to buy a factory inverter, but if you nevertheless decide to make it, then do a full-sized inverter and don't save on cooling. I previously had experience in building a welding inverter, which work at single-ended mode. I have 2 videos to this topic. Links to them will also be in the description. By the way, this inverter is still without a case. This kit is built in the same way. In the description you will find a link to the forum where the circuit was developed. There you will find answers to all questions. It was an introduction. Now let's go to the point. This is a single-ended forward converter. All is controlled by the chip of the current mode controller UC3844. The output of the chip through the driver controls the IGBT transistor. The circuit is equipped with a soft start and overheating protection. Current feedback is realized through a current transformer. In past videos, I partially explained how this works. In my case, all power components, a transformer, a choke, rectifiers, a switch, transistor, and an input circuit are on the same, so to speak, motherboard. The control circuit is on a separate board, and there is a separate standby power source. This power supply produces 15 and 24 volts. 24 volts feeds all control circuits and soft start relays. 12 volts feeds the fan. Control circuit. More than half of the components of the circuit are on this compact board. In the author's version, the entire circuit is assembled on one board, in my case, so that to minimize the size, the control was transferred to a separate board. The board was developed in about an hour, and I have to admit that I had to neglect some wiring topology rules in favor of compactness. As a result, the board is very compact. It is extremely difficult to do less if you use usual components and not SMD. The mounting is very tight and there is only one jumper on the board. You can send your board design to the factory and as a result get beautiful industrial printed circuit boards. The GLC PCB factory is one of the leaders in the production of industrial printed circuit boards with many years of experience. Orders of PCBs start at the lowest prices from $2 for 10 pieces. GLC PCB will produce for you printed circuit boards of any complexity of sizes and shapes. A link to the site can be found in the description. After assembly, the board was checked. A voltage of about 30 volts is applied to the input of the stabilizer. We connect the oscilloscope probe on the driver output and observe a beautiful meter with a frequency of about 30 kHz and about 44% filling. The control board is ready. This part doesn't need additional adjustment. If everything is assembled correctly, the components are operational and there are no accidental short circuits on the board. The original circuit operates at a frequency of 30 kHz. At first, I wanted to raise it, as well as to get more power from the core by changing the ratio of the number of turns of the windings. But the final calculations showed that even at 30 kHz, it is easy to get from the core the power about 2 to 2.2 kW. This corresponds to 80 to 90 amps of current, taking into account the voltage drop during welding to about 24 volts. With this in mind, the device can cope with 3 mm electrodes without problems, but in sake of insurance, in my unit, the maximum current is limited to 80 amperes. Since the device was made for small output current of 80 amps, which is enough for a 2 mm electrode, the transformer seems small, but I assure you it's enough, although it works almost to the limit of its capabilities. The circuit is single-ended, and it is clear that between the halves of the core, a non-magnetic gap of 0.1 to 0.2 mm is needed. Such a gap can be made without problems if you use a core of two halves, for example W-shaped. But the problem was that I didn't have such a core with a required overall power. More or less good cores were ring type. Here are sizes. Such a core will work perfectly in a push-pull circuit, but in a single-ended a gap is needed. To get gap, at first we make the markings. Secondary, we must sew the core, but not completely. Half a millimeter is enough. Next, we put the core on wooden blocks as shown. Then, at the center of the cut, we put a metal rod and neatly but hard beat it with a hammer. Unfortunately, I didn't shoot this process, but I think the principle is clear. As a result, we get two equal halves. Next, I took a check from the ATM, cut two strips and glued it on one of the halves using superglue. No need much glue. We tighten the halves of the core, for example, with Kapton tape. In general, this core has insulation in the form of paint, but additional insulation will not be excessive. Now we wind the primary or mains winding. In my case, a 1.2 mm wire is used. The calculation was made by the program. Of course, in the case of other cores, you get different winding data, so no sense of indicating the number of turns. The loops are uniformly stretched throughout the ring. Above it, we wind the insulation and then wind the fixing winding. The number of turns is the same as in the primary winding, but the wire is thinner. I used a 0.3 mm wire. It is necessary to wind it so that the turns of the fixing winding are between the turns of the primary. I forgot to say that it is very important not to confuse the beginning and the end of the winding. On the circuit, they are indicated by dots. The beginning of the winding is preferably marked, and I used a red thermo shrink for this. We again put insulation at the fixing winding and wind the secondary. It is wound with Litz wire, consists of 80 parallel conductors of 0.22 mm wire. It was additionally insulated with Kapton tape. A current transformer was wound on a small ring ferrite magnetic core. The permeability of the core is 2400 and its dimensions are now in front of you. First, the core was insulated with Kapton tape, and then a secondary winding was wound. The number of turns is about 80. A wire with a diameter of 0.24 mm was used. The winding is evenly stretched throughout the ring. Primary winding consists from one turn with a double wire of 1.2 mm. Seems that's all with this part. Output choke. From past experiments in practice, I saw how the welding devices working with and without a choke. With a choke, the arc ignites without problems, even at low output currents. This ring is taken as the core. The material here is most likely powdered iron. Ferrite isn't suitable here, at least without a gap. The ring has a light green-blue color. It is specially designed to work as an output choke. The dimensions of the core are now in front of you. Of course, it would be worth using a larger core, but my choice was limited only by this one. A Litz wire was used for winding. This is a bundle of 80 wires insulated from each other with a diameter of 0.22 mm each. That is exactly the same as in the case of the secondary winding of the transformer. The inductance of the choke is about 35 microhenry, and this isn't enough. It is desirable to have the inductance from 80 to 120 microhenry. The ends of the choke winding were cleaned of varnish, tinned, and we put it aside for some time. A few words about the components. The input electrolyte is 450 volts with low internal resistance from a good manufacturer. The capacitance is 470 microfarad. In principle, it's enough. The relay in the soft starter circuit is full size, 30 ampere, like in large inverters, although the board was originally designed to install a more compact relay. The power IGBT transistor and the diodes in the high voltage converter circuit are exactly those that indicated on circuit, no deviations. In the output rectifier used high-speed diode assemblies STTH6003. I hope they should work okay. In such assembly are two diodes with a current of 30 amps each. The cathode is common. The anodes are also connected in parallel. As a result, we get an analog of a 60 amps diode. The reverse voltage of the assembly is 300 volts. In general, here you need to use a diode with a larger current, about 100 amps. The assemblies are mounted on a common radiator. The substrates aren't isolated because cathodes are common. The output plus will be taken off from the radiator. Perhaps this isn't the best solution and it would be worth to remove current from the middle terminals of the diodes. As an input rectifier, used ready diode bridge KBG2510 with a current of 25 amps and a reverse voltage of 1000 volts. Yes, you could use more powerful bridges, but for our inverter, such a rectifier is enough, and the dimensions of this bridge are much smaller than those of more powerful ones. Of course, the bridge will be installed on the heatsink. Resistor in the soft starter circuit can be from 10 to 30 ohms, about 5 to 10 watt. Standby power supply. I remind that in the original circuit, there is no standby power supply. There a self-feeding winding is applied, which is wound on the main power transformer. In my version, I didn't do this because on the self-feeding winding, I received a noticeable voltage drop. And I was afraid that voltage might not be enough for the correct operation of the control system. Therefore, a separate low power source is used. The power of the standby source is small, about 7 watts. This is a ready-made power source of a universal type, which was purchased on AliExpress and is designed to work in induction cookers as a standby source. It produces 3 voltages, 5, 12, and 18 volts. The output voltages are set by a linear diode at 18 volts. I replaced it with 24 volt, removed the 5 volt circuit, replaced some of the output capacitors with higher voltage ones. As a result, the standby source gives out 2 voltages, that is 15 and 24 volts. The first voltage is needed to power the 12 volts fan, and the second powers the control circuit and relay. Such a standby source has a soft start, protection against short circuits. It is built on only one chip. Often it is Viper 12 or similar. Cooling radiators are taken from computer power supplies. Given the presence of active cooling and maximum welding current, they are enough. Yes, it was possible to put bigger radiators, but in this case it would be necessary to sacrifice compactness. In addition, we aren't going to work with this unit without respite. About start and adjustment works, I spoke in detail in mentioned videos, so anyone interested can watch. I will say that to my surprise, the device started working immediately without any deviations. The first start was made through a 100-watt safety lamp. The oscilloscope shows that everything is fine. The shape of the pulses on all windings is correct. The open circuit voltage is about 60 volts, which is enough for a good ignition of the arc. In addition, we have a choke. Perhaps the most important thing is checking the operation of the current limiting system. First, I set the current regulator to a minimum, connected oscilloscope clamp to the gate of the power transistor, and make a short circuit at the output. We see that the duration of the control pulse decreases sharply. The current is limited. If this doesn't happen, we must interchange the beginning and end of the secondary winding of the current transformer. Some power tracks on the printed circuit board are additionally reinforced with copper tapes. The output terminals were borrowed from my first inverter. At first they stood in a powerful 12 to 220 volt converter. Transformers, a choke, and a pair of vertical boards were glued to the main board using epoxy. Loaded with ballast, the inverter gave an honest 80 amperes. The minimum current was made about 20 amperes with the confident ignition of the arc. Due to the low minimum current value, even thin metal can be welded. By the way, the open circuit current, that is, the current consumption from mains without a load, is around 170 to 200 milliamps. The open circuit voltage is 60 volts. Well, now let's look how does it work in practice. The electrode is 2.5 millimeter. Works even with 3.2 millimeter electrode. It's ugly, I know, but not device is guilty. I don't have time to learn welding. This made an experienced welder by the first attempt with this device. You should have seen how he laughed when he saw this unit. He thought I was kidding, and it's just a compact charger, but not welding unit. It seems I have told and shown everything. There is no need to speak about the practical meaning of this construction. Well, if you wish, you can move it into a more bulky case. Put a powerful fan with bigger radiators and get a very good inverter that can compete with industrial units. But this baby is good in its own way. Well, look at it. The dimensions are even tiny for the charger. But it is the full welding unit. What can I say at the end? The task is completed. This is the smallest full-fledged inverter, and it is unlikely that you will find an industrial device with similar characteristics but smaller. Not because the Chinese cannot do this, but because there is no point in this, and I admit, but I won't stop being proud of the device. After all, it's cool. At this, friends, video comes to an end. Please don't forget to rate it and share it with friends if it was useful. Let me remind you that you will find all the necessary links in the description. Now I have to say goodbye. Until next time, with you as always was Kasyan TV.